ATP is required to transfer messages, but yeah, this is of course correct. But what would be the next hypothesis? But in what way? Remember, with an ATP analog, it's stick to the channel. ATP analog is structurally related to the channel hydrogen. So that means if in order for this carbo to move, it needs to detach from the hydrotubule. And that detachment depends on the So if the hypothesis is that you need to have some kind of motor protein that move, that carry the vesicle along the hydrotubule. And what you expect is if you have the ATP analog, it stick to here, channel hydrogen. It will be stick, and here it binds very tightly to the microtubule. If then you add ATP to ATP, then display these guys here, binds here, and then because it's inside cells ATP, and then we hydrolyze it and phosphate. Now what happens is this guy detach from the microtubule. So the idea therefore, if this is a motor protein, we anticipate that its binding to the microtubule will be depends on the we add AMP, this motor protein will stick to the microtubule. Add ATP, it will be released from the microtubule. And you can therefore purify. You can separate the microtubule and those the protein, you will be able to purify this stuff if you add ATP to the reaction. So because of this observation, therefore, Long Bear, which is actually a famous people who do a lot of work on and also kinesis, actually discovered kinesis. So this is actually the microtubules, and then you add the supernatant from the X. And then you add the AMP, PMP, and in that particular link, you add the ATP. And then there is hydrolysis. You see a very faint band here, which is roughly about 120,000, and this is kinesis. So this kinesis only happens in the supernatant soluble fraction when you first have AMP, PMPs, and then AMP. Very specific. When they try to isolate this protein and see what happens, and then they so now kinesis turns out to be highly complicated. So first of all, there are actually many different show you in a minute. But there is one thing called the conventional kinesin, which is represented by one particular family of kinesin called kinesin 1. The kinesin 1 is, consists of 4 different proteins, which have 2 heavy chains and 2 light chains, so altogether 4 proteins including complex. And this is the case. And the 2 heavy chains actually consist of the head region and then a linker which actually is this immediate short segment, just immediately after the head. And then you have a very long stalk and the tail. So all different from the heavy chain. And then at the tail you have 2 light chains. So the 2 light chains you find here. And this is the end terminal of the heavy chain. This is the C terminal. So the N terminal usually is regarded as the so-called motor domain because this is actually the part that directly binds and is responsible for the movement. And this linker region is actually very important, as you will see in a minute. But the C terminal tail is actually the one that binds to the carbon, as illustrated in this particular schematic diagram. So this is the N terminal motor domain. linked stock in the superlunar tail with a light train, and this is the recipe that's carried by the kinesin. Now there is something called a kinesin receptor, which actually is the one, is another protein, so it's actually not part of the vesicle, it's a protein that can associate with a certain type of vesicle. And it is believed that this kinesin receptor is the one that controls electricity. So certain kinesin are able to bind certain cargo. And the reason is because certain kinesin can specifically recognize the kinesin receptor, or sometimes we call it a receptor. And then the whole thing starts moving along the microtubules. And then one very important thing that you have to remember about kinesin movement is that it always, I shouldn't say always, but most of the cases, you carry cargo towards the plus end. So plus end here, minus end here, kinesin carry the cargo only in one direction towards the plus end. So how kinesin can move along the microtubule? So it has been described as something called processive movement, meaning that the two heads, remember that diamonds was two heads, so each head is three heads one head. So two heads kind of moving step or walk over each other. But at any given moment, there is always one head that attached to it, and this is the trailing head. The trailing head actually binds to AET, and the leading head starts to move when it binds to AT. So remember one thing, we talk about microtubule polymerization, we use PTP. But in the case of kinesin movement, it depends on AT. Okay. Now what happens is that when the leading head binds to ATP, it will trigger the conformational change such that the linker region, so this is actually the linker region, will change, and then at the same time, this trailing head is loose, so it no longer binds to the microtubule anymore. It becomes loose, and this change of conformation of the link try to swing the trailing head forward. So this is the leading head, the trailing head. There is conformational change, and also the ADP release the trailing head to be loose. So now it starts to off from the microtubule and swing to the other side towards the plus end. And once it goes to the plus end, then it will bind to ATP and start to move side. So you can see that this process of movement of the microtubule motor domain depends on ATP hydrolysis, because only the ATP binds to it, will be stick to the microtubule, and without the ATP when it binds to ATP, it becomes dissociated from the microtubule and they go to. So you cannot just stick the whole thing. You cannot just have the head continuously stick to the microtubule. It needs to pick off from the microtubule, and that depends on the change of ATP. And also from this diagram, you realize that every step, so this is one step, right? So you went from here to here. So every step, the distance is 16 nanometers. So this is 8 nanometers, and this is another 8 nanometers. So each step spanning twice the diamond. So as a result, you have a step of 16 nanometers. So that each step of the times is always 16 nanometers towards the plus end. It's actually very different. So kinesin is always 16 nanometers. Now one more interesting thing is that you have to remember when the kinesin bring a cargo to the destination, let's say an exon, once the destination is reached, the cargo needs to be unloaded from kinesin from the tube. In that case, the vesicle is being unloaded. And now the kinesin will change the conformation, so it's kind of fold inside. So this is actually the head, and this is the tail. So initially it's kind of like a sketch like structure. Once the cargo is unloaded, it becomes kind of folded inside. So as such, it actually tries to prevent continuous ATP uptake. It makes sense, right? If you imagine the kinesis is like a chain, once the chain has certain people with the acceleration, you don't want the chain to keep moving with the energy that they make. So this, as a result of this inactive kinesis, is no longer able to hydrate. So there are altogether in human genome 45 different kineses. When I say conventional kinesis, it's mostly referred to the kinesin 1, which is actually a family. And there are altogether 14 families, or 14 classes, 45 families. And they are actually structurally very different and can have different functions. In some cases, they can have different cargoes. And in some extreme cases, they might not even be involved in transport at all. So for example, remember I mentioned kinesin 13. So if you look at the structure of kinesin 13, it doesn't have those stop and C terminal here. It only have two heads. And its function, as I mentioned in the previous lecture, is for capacitor. It promotes capacitor. It wasn't involved in transfer of carbon. So in some cases, they might not even involve in transfer. So for kinesin 5, it doesn't have like a C terminal tail, but it has two end-to-end motor domains. So the function is for binding. It's not for transfer. So I guess this might happen during mitosis. Now, one more thing about kind of exception to kinesin is the kinesin 14, which seems to move towards the minus N. It's not even. So that's why in one of the previous slides, I said that mostly carry cargo towards the minus N. But there is one exception. That case is the kinesin 14, which actually moves towards the minus N. So different members, and they can have very different functions. Structurally, they also different. How about the diamine? But the diamine actually is very different in terms of structure from the kinesin. It's much larger than kinesin. So the kinesin everything is about 120 kilodalton. For diamine, it actually consists of six, two large subunits, smaller subunits. And if you just look at one single large subunit, its cell is already around 500 kilodalton, which is very huge. And if you look at the structure of the large subunit, it looks something like this. It has six ATP binding domains, 1 to 6. And then in between there is a stop region. So it's actually the whole protein fold into something like a flower structure. The flower is consisted of all those 6 ATP binding domains, and then you have a stop that binds to the microtubule. So the stop is the one that binds to the microtubule. And then there is a linker region just next to the ATP binding domain number 1, which then associates with the whole N-terminal region called the stem. Now the stem actually is involved in binding to other subunits. So as I said, this is the large subunit for diamine. The function is also need to bind to other proteins, which I will talk about later. So this is actually the stem region which binds to the other proteins. But the motor domain that is sufficient for us to understand the movement along the microtubule is all found in the large subunit. So why the diamine can actually move along the microtubules, and how does it move the power? So it was believed that, again, it depends on ATP binding. And when there is ATP binding, there is a conformational change that mainly happens in this linker region. So this is a linker region. And this linker region will have a very drastic change in conformation when it binds to this. And as such, it was believed that after that conformation change of the linker, the timing make a step forward because on microtubule, and later on when it became hydrolyzed, the whole thing kind of moved back to its original position, and as such, tried to push the carbon towards the pipeline. So actually, you can find it in the YouTube. There are two YouTube videos that I found which explain a lot better than the textbook. And in particular, I would suggest watching this particular YouTube from video, which is rather long, but you can just go to 32 minutes and start to watch the movie, which illustrate how time moves. So if you have time, I strongly recommend you to actually watch the entire video. Anyway, just here look for this particular movie, which explains how it works. So this is the carbon. This is actually the stock is here. Like what you define. So we have two branches of unit. Now this is the linker region, which change parameters there is a conformation region. So if we go back to this, so initially, the yellow means it's the linker region in a conformation which the binding has not bound to AT. So this is bound to AT. And this is the stock, this is the microtubule binding. It's kind of like this. So you have a flower-like structure, and then it usually the one binds to ATP, so this is ATP. Once it's bind to ATP, then see what happens to the linker region. The linker region initially is yellow. Now there is a restriction of the linker region, and the whole thing kind of like making a step toward the cascade. So from this kind of conformation, it's changed, something like this. So you still have this flower-like structure, but it's kind of like a step forward, step towards the cascade. Then there is ATP binding. Then after the ATP becomes hydrolyzed, it returns to its original conformation. Returns to the original conformation, and then it tries to push, pull the carbon towards the cell. So from this, straight conformation, and then it goes back to this. So when it returns back to this conformation, it's kind of pull the carbon towards the cell. you're interested, you can actually watch a video at home. There's another one which actually very short. It's kind of similar, even though in that particular video it's the hydrolysis in that the initial or surface. So this is actually just the diagram that I write down. Initially, the linker is kind of that information, confirmation, but when there is an ATP bind, it will step forward. And after it step forward, it will then pull the whole carbon towards the plasma. And also one thing, remember, like the kinesis, whenever the motor needs to move forward, it needs to first detach from the microtubule. So initially it binds to microtubule. But when it makes forward move, it needs to first detach from the microtubule and then bind it a more forward position. So I can actually update the PowerPoint. I just want to yesterday. Better than the original picture. So ATP binding trigger this conformation routine and then we move forward towards the plasma. So this is only the motor, the large subunit. But in order for the whole thing to work, it also needs to bind to other proteins. So the other proteins are called dynactin, a P150 unit, and a protein called dynamicin. So all together you have, in addition to thymine, three other proteins, dynactin, dynamicin, and P150. The whole thing from a complex and then attached to the cargo. So the dynamic in actually is the protein that try to hold everything together, holds the dynamicin, P150 together, and then into the dynamic. So one way that is actually very useful for people who want to look for or to study intracellular transport is whenever you try to express your cell dynamically, for some reason you can actually disrupt the whole thing and then disrupt the dynamic. So in other words, you can actually try to use it as a way to always resting dynamically alone inside a cell to see whether a particular transport process can survive. Because when you see something move, you can say, oh, maybe do kinesis, maybe do tiny, maybe do mouse, which are associated with that. So how do you know that a specific transport process inside the cell depends on the tiny one simple way to do it is actually to always rest dynamically. It disrupts the whole process, and if, as a consequence, you disrupt the cellular transport, and you can say that this process, this transport, depends on time. So go back to the original question that I mentioned, that how the transport in terms of direction, will the transport, whether the transport. So which cargo, whether it goes to the end the transport or directly redirection, what determines the direction of the transport? So it is indeed the orientation of the microtubules. So remember in a very early slide, in the first lecture, I talked about in general the orientation of the microtubule is such that the center, which has the centrosome, has the minus n microtubule, and the microtubule go with plus n towards the periphery. So in other words, we can imagine that for those cargoes, such as ordinaries that move towards the periphery, it will move towards the center, and it will be carried by the mechanism. And for those ordinaries that need to move from the periphery back to the center of the cell, it is mediated by time because it is towards the negative n, in that case, towards the centrosome. So this is actually just a couple of examples showing that the Golgi apparatus actually move in close vicinity towards the centrosome. So the Golgi actually is being carried by the diamond along the tubule. On the other hand, if you have circulatory vesicles, such as this one, after a sample in the Golgi apparatus, it needs to go to the cell periphery, go to the plasma membrane, and release its content in order to So the circulatory vesicle need to actually move towards the periphery, and in general, it will move towards the plasma every 5 times. So which direction of movement, that is, are carried by timing or kinesis, depends on the orientation of the movement. So in general, microtubule towards the cell periphery is plasma. So in that case, you can imagine that it is general to say the so as this example, which is say kinesis is responsible for urinary transport, and timing in general is for respiratory transport. Now, there is an exception to it. What is the exception? And that is go back to the neuron again. So in one of the early slides that I showed you yesterday, in neuron, the dendrite is undertaken because in the dendrite, the orientation of microtubule is mixed. So it's not always the plus n in the periphery. There are cases in which the minus n is on the periphery rather than the central of the cell. So as such, you can imagine that the transport in the dendrite is a little bit more complicated. So that could be an example in which the kinesin will actually move the cargo towards the center. So these are the microtubules that has the plus n distal to distal hormones periphery. But the blue ones are the ones that have the minus n pointing towards the periphery. So you can imagine that if a cargo actually moves along the blue microtubule, what happens is that the kinesis will actually bring the cargo back to the center of the cell. And the thymine will move the cargo towards the cell periphery. So even though the previous slide I say that in general, kinesin is on the transport, moving the cargo towards the periphery, thymine is for rapid transport, moving cargo back to the center of the cell. But at least in the case of the dendrite, because of the orientation of the microtubules, it could be completely opposite. The kinesin mediated rapid transport, the thymine is over. So finally, I just want to bring the question that in internet they help you to answer my second question. So from those schematic diagram, it seems that you only have one cargo and one motor. So each cargo is carried by one motor along. This is something that you always ask for. So what I want you to look for the information in the next couple of days is it true? Is it always one cargo, one motor? And a cargo is simultaneously linked to two motors. And what happens? It's something that you might want to look Finally, this is just a assignment question that I want to put in the Moodle. So as I mentioned that if you do that kind of experiment, you realize that along the axis of the neuron, the velocity of transport of the vastly different. So it could be almost 2 or 300 more in some cases than the others. So we call this the fast transport, and there are slow transport, and also there are cargoes that have to move the velocity. first thing I want you to do is try to give an example. You can just give one example for each. So fast transport, slow transport, intermediate transport, along the axis that you want. But the important point I want you to do in that particular question, and that's actually why I want you to do this question, is I want you to think without talking any detail, without really going to the detail. Just based on what I talked about these 2 or 3 lengths. Just to think about the 3 different possibilities. How can a cell move different targets by different velocities? You don't even need to know anything about biology. Or you can probably already be able to just draw some hypothesis. What could be possible explanation? Why some can move so far, some move so slow. And then the last part is what is the current understanding of the fast and slow motion? What has been found? What has been found recently that can explain the fast and slow motion? Now, your hypothesis can match with what currently we know, or your hypothesis can be completely wrong. I can still give you marks as long as you actually raise a sensible hypothesis. I will give you marks, regardless of whether it's true or not. But at the end, I want you to actually find out from the paper research, paper literature, what is the reason, what people now believe. And then also, please try to include